When talking about line maintenance on live lines or de-energized lines, the same rule applies. Safety is always first. Many people assume that de-energized maintenance is much safer, and in some ways it can be, if the proper temporary grounding equipment is in place. However, accidents do happen and lives have been lost while working on de-energized lines due to inadequate temporary grounding practices. The goal is for all linemen to return to their homes at the end of the workday alive and well. There are industry standards, company policies, and work rules, but it comes down to the individual lineman choosing to follow the rules and taking responsibility for his own safety. Talking about temporary grounding for de-energized maintenance is really talking about protecting the lives of linemen. A lineman may work 10 or 20 years or even longer and never experience a fault current, but without warning and when least expected, one can occur. Without adequate equipotential grounding correctly installed, the lineman can lose his life in a fraction of a second. Temporary grounding is protection for his life. There are a number of reasons why fault currents occur. First is human error, such as the closing in of a switch that should have remained open. Today's safety rules and procedures are intended to eliminate human error. However, humans make mistakes and will continue to do so. Second, lightning is also a concern. The storm does not have to be overhead for lightning to strike. In fact, it can be as much as 10 to 20 miles away. A few years back, a utility company was out working in their training yard. They saw a storm off in the distance and came down off of the poles. Right after they had climbed into their trucks, lightning struck one of the poles they had been working on. Third, backfeed is another concern. There could be solar panels, a generator, or some other energy source downstream on the circuit. Fourth, there have been cases where a de-energized circuit accidentally comes in contact with an energized one. An example of this is when a car crashes into a nearby pole and the energized circuit falls across the de-energized one. Fifth is induced voltage. In the photo, you will see a fluorescent lamp illuminated. This lamp is illuminated solely by the induced voltage from the transmission lines. Any time when working close to another circuit that remains energized, there is a risk of induced voltage. Induced voltage has been the cause of many accidents. Around the year 2000, a lineman in the USA was killed working on a de-energized line. There were approximately 300 volts of induced voltage on the line from an energized 345 kV line across the right-of-way, resulting in his death. Whatever the reason, fault currents have occurred and will occur. Linemen need to be protected against them, and this is done with proper temporary grounding. The purpose of proper temporary grounding is to protect the worker. There are two essential components. First is to create an equipotential zone to minimize the voltage drop across the worker. Second is to provide a low impedance path to ground to engage the system protection devices as quickly as possible to clear the fault. If the fault is not cleared, the worker could be exposed to current for a prolonged period of time, increasing the risk of injury or death. And the fault current duration may exceed the capacity of the temporary grounding equipment, resulting in failure. As a manufacturer of temporary grounding equipment, Hubbell Power Systems has performed many tests against industry standards to ensure Chance grounding equipment complies with the specified ratings. Ground sets are sometimes pushed beyond their limits to see what they are capable of handling. This video will show what happens when ground sets fail. Keep in mind, these testing failures were experienced in a laboratory setting to help avoid them in the field. If the ground sets fail, the lineman could lose his life. For this reason, it is vital to use adequate temporary grounding equipment and to ensure that the equipment is properly installed, creating an equipotential zone and providing a low impedance path to ground. Assuming the ground equipment is adequate and does not fail, the next concern is the amount of the current that will flow through the lineman in contact with the circuit during a fault current. The fault current will divide between all paths to ground. Some current will pass through the lineman if he is in contact with the circuit and a second point at a different potential. There have been many studies conducted on the effects of electrical current on the human body. The results for many of these studies are quite similar. In these studies, the results indicate that with only 6 to 16 milliamps of current, there is a painful shock and the person is approaching the point of not being able to let go. With only 17 to 99 milliamps, the person reaches the point of extreme pain. not being able to let go, and his ability to breathe is impacted, making death possible. To look at this another way, if we had a 10,000 amp fault current, which would fall into the lowest ASTM grade, it is only 0.00017% of the fault current that can put his life in jeopardy. That is an extremely small percentage of the overall fault current. Because it takes so very little, it is very important to do everything possible to minimize the current that flows through the lineman. The key to minimizing the current that flows through the lineman's body is to minimize the difference in potential across his body. This is done by minimizing the resistance of the temporary grounding equipment in parallel with the lineman. Remember, the current divides inversely proportional to the total resistance. Therefore, reducing the resistance of the ground set in parallel with the lineman will minimize the difference in potential, thus reducing the current through the lineman. So how is this done? There are some key considerations for proper temporary grounding and the minimization of the current that will pass through the lineman. The earlier video showed what happens when the temporary grounding equipment is inadequate for the level of fault current. It is also very important to take care of and maintain this equipment, and to install it properly in an equipotential configuration. Each of these will be reviewed in detail. There are 3 concerns resulting from a fault current. Sometimes attention is only given to the electrical current, but the resulting mechanical forces and heat are also of great concern. This slow motion video shows a ground set experiencing a fault current. The test in the video had a duration of 15 cycles, or a quarter of a second. In real time, the cable is whipping around so fast that there would not be time to get out of the way. Anyone close to the cable could be seriously injured. There were also fireballs at both ends resulting from the extreme heat. The ground sets must be adequate to handle all of these forces. By the way, this ground set passed the test. So how are adequate ground sets selected? The maximum available fault current and its duration, and the asymmetrical factor, or X/R ratio, must be known. This is the fault current that the worker must be protected against. Although it is not uncommon for temporary ground sets to be requested for a specific voltage, such as for 33 kV, 220 kV, or some other voltage. It is important to remember that ground sets are rated for fault current, not for voltage. The maximum available fault current and X/R value will depend on many factors, including the design of the system, proximity to substations and generation, and other factors. If the utility does not know the maximum available fault current and X/R value, it needs to find out so adequate equipment can be selected. They should be determined by a qualified engineer. This should also be reviewed periodically, especially after any system changes that could impact the maximum fault current level. The lowest rated component of the ground set must be adequate to handle the maximum possible fault current. A ground set with ASTM Grade 5 clamps and ASTM Grade 2 cable only provides ASTM Grade 2 protection. The amount of asymmetry in a fault current will vary depending on the X/R value. The asymmetry causes the initial peak to be higher, with subsequent peaks diminishing until it reaches the asymmetrical level, or until the fault clears. With a very low X/R value, the fault current will be nearly symmetrical. With a high X/R value, the peak can be up to 2.5 times the symmetrical current, or even more. A fault current with high asymmetry will have substantially more severe mechanical forces than a symmetrical fault current. For that reason, it is very important to understand the potential amount of asymmetry at the worksite, and ensure the temporary grounding equipment is capable of handling the resulting forces. The 2 primary industry standards for temporary protective grounding equipment are ASTM F855 and IEC 61230. As these standards are periodically reviewed and updated, please refer to the current version for each standard. ASTM has specific grades, 1 to 7 and 1H to 7H. The rated and test fault current levels for these grades are provided in 2 tables. ASTM F855 Table 1 provides withstand and ultimate fault current levels for grades 1 to 7. This table should be used when the asymmetry factor is less than 20%, or an X/R ratio less than approximately 1.8. This is a nearly symmetrical fault current. With a maximum available fault current level and the duration, we can determine from the table the grade of clamp and minimum cable size needed. For example, with a fault current level of 25,000 amps for less than 15 cycles, based on withstand ratings, a minimum of grade 3 clamps with 2-aught copper cable would be needed. ASTM F855 Table 2 provides the rated current and minimum peak current test levels by cycle for grades 1H to 7H. Table 2 only provides an ultimate rating and should be used when the fault current level asymmetry factor is greater than 20% at the worksite, or when the X/R ratio is higher than approximately 1.8. Higher levels of asymmetry are common when working in or close to substations, but can exist in other parts of the system also. The asymmetrical factor should always be considered when reviewing fault current levels for a worksite. The testing for ASTM grades is based on an X/R of 30. This creates a first cycle peak of 2.69 times the rated current. For IEC 61230, there are no grades. The manufacturer may select the rated fault current level at which they would like to classify the grounding set and perform the testing. For IEC testing, the symmetrical test current is 115% of the rated current. The current peak on the first cycle is 2.6 times the test current for ground sets to be used on systems over 1,000 volts, and the duration is up to 115% of the rated duration. For example, for a classification of 15,000 amps, it would be almost 45,000 amps at the peak of the first cycle. It is important to use appropriately rated ground clamps for temporary grounding. Tap clamps like the one on the left do not have the mass and design to handle the high levels of current, heat, and mechanical forces associated with the fault current. A tap clamp is designed to carry continuous current of a few hundred or so amps, not thousands or tens of thousands of amps that come with a fault current. The tap clamp would be blown to pieces. The ground clamp on the right is much larger and has much more contact surface area to make a lower resistance connection. It also has 2 connection points to secure the ferrule and cable. To select clamps, first ensure the clamps are properly tested and rated to handle the maximum available fault current, with its corresponding asymmetry and duration. Also, select the appropriate type of clamp for the application. For example, if connecting to a flat surface, do not use C-type clamps or duckbill clamps because there will not be a good connection, and in the event of a fault current, the clamp will very likely come off. Instead, use a flat face or tower clamp designed for connecting to a flat surface. In some cases, there are options. To connect to a round conductor, there are C-type, duckbill, or all-angle clamps. In the first video, an ASTM grade 5 ball stud clamp was tested to see if it could be rated at a higher grade. The video is in slow motion. In the video, the clamp was glowing red inside from the heat and split in two as it could not handle the heat, mechanical, and electrical forces from this higher rating. This is the same test, but in real time. The ferrules and heat shrink are also important. If a bare cable is attached to a clamp, it will have a number of issues. First of all, when tightening the connection to the clamp, cable strands could be damaged. It may only take a few broken strands to significantly impact the current carrying capability of the cable, resulting in a failure. Over time, the movement and handling would also damage more cable strands. Second, there would also be oxidation and contamination, all resulting in a higher resistance connection. The damaged cable would not meet the cable's original rating, and it may ultimately fail. The higher resistance or failure could result in serious injury or death for the lineman. Third, ferrules are used to make a solid low resistance connection. In the photo in the bottom right-hand corner, it is not visible where the ferrule ends and the cable begins. In the photo just to the left, the difference can be seen because it is an aluminum ferrule. Fourth, the ferrules also help to absorb some of the mechanical force as shown in the slow motion video. As the mechanical force came down, the ferrule bent. It takes a significant amount of force to bend that ferrule. The ferrule bending absorbed some of the mechanical force, so it did not all impact the clamp. The heat shrink is also important. It helps keep out moisture and contaminants, resulting in less corrosion and resistance. It also provides stress relief for the cable. The heat shrink adds rigidity where the cable enters the ferrule, while still allowing some bend. This helps absorb some of the mechanical forces. In addition, for an unshrouded ferrule, it minimizes the bending where the copper strands of the cable are in contact with the edge of the ferrule. The cable should also be rated for the maximum level of available fault current with its corresponding asymmetry and duration. As discussed earlier, we need a low impedance connection to ground to operate the system devices and clear the fault current as quickly as possible. If the fault current does not clear, the heat will continue to increase, and the cable could reach its fusing point in a matter of cycles. This first video will show what happens when a cable is undersized or what may happen if the fault current does not clear. It is very evident from this video that an undersized cable will fail quickly and leave the lineman unprotected. Standard grounding cable per ASTM F855 should be stranded soft-drawn copper conductor. The IEC 61230 standard allows for copper, aluminum, or aluminum alloy. However, per IEC 61230, The selection of aluminum cable should be made carefully and include precautions for storage and inspections before use. These additional precautions are necessary because aluminum damages more easily. The current carrying capacity of aluminum versus copper must also be considered when selecting cable size. Based on information provided in IEC 61230 and as seen in this table, for a 95 mm squared aluminum cable, the current carrying capacity would only be 16,700 amps versus 25,500 amps for copper. That is less than 2/3 the current carrying capacity of the copper cable. In other words, to have the equivalent current carrying capacity, you would need a larger aluminum cable. For these reasons, Hubbell Power Systems as a manufacturer only recommends soft-drawn copper cable. The length of the cable must also be considered. It is important to minimize the cable length because resistance increases with length. However, that does not mean the cable should be taut. If it is taut, the mechanical forces could break it. Some slack is needed. The IEC 61230 guidelines recommend the cable should be between 1.2 and 1.5 times the distance between the installed clamps. The cable length should also be taken into consideration because of the whipping effect that can result from excess cable during a fault current. The whipping cable can hit and injure a person or impact the structure, resulting in damage to and potential failure of the cable. The whipping effect can also increase the mechanical forces and result in a failure as seen in this slow motion video. The cable came up and then back down just like a whip, and the cable failed right at the cracking point. This happened in less than 1/4 of a second. As a side note, this was a new type of cable that Hubbell Power Systems had not tested previously. The engineer running these tests believes the cable failed because it may have had broken strands. The following slides will show that the cable length can mean the difference between going home for the day and possibly losing your life because of the increased resistance resulting from longer cable. In this example, a ground set with a 3-meter 1-aught copper cable is being used to protect against a 10,000 amp fault current. Based on Kirchhoff's law, the current that would pass through the lineman is 13 milliamps. If the cable length is increased to 7.6 meters with the same 1-aught copper cable and 10,000 amp fault current, the current passing through the lineman increases to 27.7 milliamps. His life is now in danger. For this reason, the cable length should be minimized, allowing for some slack as previously discussed. The cable size also makes a difference. With the 1-aught cable that was in the first example, there were 13 milliamps passing through the lineman. If the cable is replaced by a larger 4-aught cable, which has less resistance, the current passing through the lineman is reduced to 8.4 milliamps. The larger cable provides better protection, however, it also weighs more. If close to the limit of a grading or rating, consideration should be given to using a larger cable size. The care, maintenance, and testing of temporary grounding equipment are also very important. IEC 61230 states that temporary grounding equipment should be thoroughly inspected before each use. If any damage is detected, it should be removed from service. In addition, ground sets should be tested periodically with a tester, such as the Chance Temporary Ground Set Tester. The ASTM and IEC standards do not specify the frequency for testing temporary grounding equipment. As a manufacturer, Hubbell Power Systems recommends testing at least once every 12 months. However, the employer should determine if more frequent testing should be performed, taking into consideration the frequency of use, work conditions, care and maintenance, etc. Frequently, ground sets fail testing due to dirty clamps. Contamination and oxidation on the clamps increase the resistance. If these ground sets are failing when tested, that means they are not offering the protection they should in the field. This could mean the difference between surviving a fault current or not. For this reason, ground sets should be kept clean. The contact surfaces should be cleaned with a wire brush before each use. There are some key points to remember when installing temporary grounding equipment. As already discussed, the ground sets need to be thoroughly inspected before each use. The lineman needs to verify that the line is de-energized and should clean the clamp and all contacting surfaces, such as the conductor, ball stud, or bus, to minimize the resistance that can result from oxidation and contamination. He should also ensure that the clamps are tightened to the manufacturer's recommended torque value. In case of a fault current, the added resistance from contamination or from loose clamps could result in serious injury or death. It only takes a few minutes to clean and tighten the connections. When installing the clamps, always treat the system as energized until it is 100% grounded. This means using an insulated stick such as a Chance grip ball clamp stick when installing clamps on the conductors. Always connect to the ground connection first and remove the ground connection last. Also, make sure the ground connection is clean, tightened, and properly sized. For example, if connecting to a ball stud, make sure the ball stud is adequately sized and tightened. This slow motion video shows what happens when the ball stud is undersized. The undersized ball stud failed. This next video shows what it looks like when the fault current enters the earth. This video is a little older, but the content is still applicable today. The earth appears white because it is covered with snow. The earth is frozen at least before the tests. These tests are all at around 3,000 amps. It is amazing how the earth moves, and clearly there is a hazard for anyone nearby. Here's an example of what not to do. This driven ground rod is clearly in loose soil and would likely come flying out of the ground in the event of a fault current. It is also important to note that there is some cable still coiled on the reel. Coiled cable acts as an inductor and could melt, vaporize, or explode. Always remove all cable from a reel when installing. Now, a look at configurations. Here are 4 configurations that at times in the past, and hopefully not at the present, were commonly used. These 4 configurations are not adequate. In the first, each phase is grounded to its own ground rod. In the second, all 3 phases are grounded to the same ground rod. In the third, the 3 phases are connected up top and have a single ground set from one phase connected to a ground rod. In the fourth, the 3 phases are connected up top and have a single ground set to the neutral. So what are the issues with these configurations? First of all, in the first 3 configurations, the cables are very long. Looking at the calculations for this example, with a 12.2 meter cable, there are 42.4 milliamps passing through the lineman. This is much too high and can result in death. Second, the voltage drop across the lineman's body has not been minimized. The lineman is at a different potential than the grounds, and his hands and feet are at different potentials. An equipotential zone is created by bonding all conductive objects together at the work site to minimize the differences in potential. Remember, to minimize the differences in potential, we need to minimize the resistance of the ground sets connecting the conductive objects. On a pole, this is done by adding a cluster bar under and close to the lineman's feet and installing a ground set from the cluster bar to the phase he is working on, and bonding to any other conductive object in the work area, such as a guide wire. In the example, the cable in parallel with the lineman is now reduced to only 3 meters. The current through the lineman per Kirchhoff's law is reduced to 13 milliamps. This is a big improvement over the 42.4 milliamps. The equipotential zone around the lineman puts his hands at nearly the same potential as his feet. If his hands and feet are at the same potential, there is no voltage drop across his body, and the current does not flow through his body. In reality, there will always be a slight difference in the potential between his hands and feet, and some current will flow through the lineman. However, by using equipotential grounding, we minimize the current through his body as much as possible by reducing the resistance of the parallel path and thus minimizing the difference in potential. When climbing on wood poles, the cluster bar should always be in conductive contact with a metal nail or spike that penetrates the pole at least as far as the climbing gaffs. This is to bond to the potentially more conductive interior of the pole. For steel lattice towers, the equipotential zone is created by grounding each phase to the metal structure below the lineman. All connections need to be clean and tight. Bracket grounding is used in many places around the world. That is grounding installed on both sides of the work site. Using bracket grounding, also known as double point grounding, has some advantages over single point grounding. However, consideration should be given to the risk of creating a current loop. If using bracket grounding to create an equipotential zone, it is critical for the lineman to install a cluster bar below and close to his feet on the pole he is working on, and also a personal ground set from the cluster bar to the phase he is touching. Without the cluster bar and personal ground set, there is no equipotential zone, and the lineman may be exposed to hazardous differences in electrical potential from induced voltage or in case of a fault current. The advantages of double point versus single point grounding are: first, the double point provides an additional low resistance path to ground, allowing more of the current to flow through the grounds, thus reducing the current that would flow through the lineman. Remember, the current will divide between all past the ground, so an additional path will reduce the current through the lineman. Second, most of the current flows to the ground farther away from the work site, reducing the risk of step and touch potential at the work structure. The advantages of single point are: first, less time and work to install the temporary grounding equipment, as there are fewer ground sets to install and only one structure involved. Second, the ground sets are in closer proximity and more easily monitored. It is also important to mention that equipotential grounding is still required when working from an insulated bucket truck. Any contact with the pole or cross arm while working on the conductor creates a path to ground through the worker. Up until this point, the discussion has been mostly about the protection of the lineman working overhead. There are risks for the lineman on the ground also, and they need to be protected. The first of these risks is step potential. When the fault current enters the earth, it will generally decrease in magnitude with the distance from the entry point due to the soil resistivity. Anyone without protection standing with their feet apart and close to the entry point will have a difference in potential between their feet, resulting in current flow through their body. The current will enter one foot and exit the other. Accidents of this nature have happened, resulting in burns, amputations, and worse. In one particular case, the lineman on the ground was 8.5 meters away and had significant injuries. Safe distances will be discussed in more detail shortly. There is also the risk of touch potential. If the unprotected lineman is touching the structure, the truck, or any other conductive object that becomes energized during the fault, the lineman is another path to ground. The ground resistance will vary from place to place and even within the work zone. In this example, the earth resistance is 32 ohm meters with a fault current of 10,000 amps entering the earth. As shown, the current diminishes as the distance increases. Taking a closer look in this example, to keep the current through the lineman at or below 16 milliamps, the distance would be almost 15 meters. This is a significant distance. There are linemen on the ground who are exposed to these risks. They either need to maintain a safe distance, which in many cases is not practical, or have protection. A chance EQUIMAT is one option. With both feet on the properly installed EQUIMAT, the difference in potential is virtually eliminated and the lineman is protected. It is critical, though, for the lineman not to have one foot on the mat and the other foot on the ground, as his feet would be at different potentials. The EQUIMATs come in different sizes and can be connected together to make a larger protected work area. Insulating equipment adequate for the maximum voltage is another option. In summary, proper temporary grounding creates an equipotential zone, providing the best known protection for the lineman. Small changes such as shorter cable lengths, cleaning the clamps, cleaning the conductors, etc., affect resistance and the current through the lineman. These small changes can make the difference between a lineman suffering serious injury or death or going home for the day. Proper temporary grounding is critical. The safety of the lineman must come first.